the application of UAVs and surveying, an overview of UAVs and their relationship with surveying. There are two main hardware options with UAVs. These include fixed-wing and multi-rotor UAVs. Fixed-wing UAVs have applications including aerial mapping and pipeline and power line inspection. The pros of UAVs is that they have a long flight time, cover a large area, and are fast. The limitations are that they need a large amount of area to take off and land, are unable to hover, harder to fly, and are expensive with a cost of roughly $25,000 to $120,000. Their service requirements though are cheaper due to less moving parts. Multi-rotor UAVs have a variety of applications as well. These include aerial photography, video aerial inspection, high resolution imagery, and restricted area mapping. The pros of these instruments are that they are easy to use, they have the ability to hover, have good camera control, and can work in confined spaces. The limitations include short flight times and a small payload capacity. They are much cheaper though, ranging from $5,000 to $65,000. The service though is expensive due to many moving parts.
The operation of UAVs in Australian airspace is covered by legislation under the Civil Aviation Act, Civil Aviation Safety Regulations, and the Manuals of Standards. All UAV flights must comply with the standard operating conditions. These are: all drones must be flown below 120 meters, must remain within visual line of sight from the pilot, must be operated during daylight hours, must remain greater than 30 meters from anyone not associated with the flight of the UAV, and must comply with the restricted and prohibited airspace. All flights must also remain away from any populous areas. The higher the population, the greater the exclusion zone. They must not be operated in controlled airspace, which is dictated as 5.5 kilometers away from controlled aerodromes, and must remain out of the approach and departure paths of any runway, which usually extends 7 kilometers from the ends of those runways, and must not operate near any public safety operations such as the fire brigade, police, and ambulance. The operation of remotely piloted aircraft or UAVs in Australia is divided into a number of categories. The first question that must be asked is the flight for commercial gains? In other words, is direct economic reward received as a result of the flight? If no, then the flight is for leisure purposes. Leisure is divided between under and over 100 grams. If the UAV does weigh under 100 grams, it does not have to comply with any exclusion zones outlined by the CASA regulations. Commercial use is divided into two categories, under and over 2 kilograms. If the UAV weighs over 2 kilograms and the landowner isn't present, the operator and pilot must be accredited accordingly. If the landowner is present, then the landowner rule applies and no accreditation is required as long as the operation is undertaken on the land in question. It is important to note that all flights under the regulations must comply with the standard operating conditions. Accreditation and licensing for UAVs is a tiered hierarchy system. Any company must hold a remote operation certificate and keep a detailed maintenance log of any flights. They must also provide adequate training updates as necessary to their pilots. The chief pilot and remote pilot must both hold remote pilot licenses and operate under the employer's certificate. They must also keep a detailed logbook of flight hours. The training for the remote pilot license must include a minimum of 5 hours flight time operating the same category of aircraft as is intended to use, training in weather, emergency and system malfunctions, and a thorough understanding of standard operating conditions.
There are two main ways that UAVs are used to acquire data. These are photogrammetry and laser scanning. Photogrammetry uses several photos to create orthophotos, which are stitched together. They use mainstream cameras and produce digital terrain models. They have poor point definition and can be hindered by vegetation and weather. They also use a variety of bandwidths if required, including near infrared and infrared. Compared with photogrammetry, laser scanning has an increased accuracy and also excellent point definition. It can also be paired with photogrammetric images to produce coloured models. It also penetrates vegetation better, but produces DTMs that can be irregular and requires much more post-processing. UAVs usually use a field-to-finish software to process the data. The advantages are that they have consistent formatting throughout the whole process, all data is stored together, there is no need to transfer data between projects, and there is also no need to export, and there are a wide range of features. Field-to-finish software has a number of disadvantages. One is that it is expensive and requires lots of training. It also requires a large amount of computing power, which can cost a minimum of $6,000.
The technique comparison involves comparing total station, GNSS and UAV surveying methods. The traditional method of total station surveying is very accurate, achieving sub 5mm accuracies. However, it can be very slow due to extensive setup work required. Physical contact with the area is also a must and can be detrimental for volume determinations. Post-processing is also required and slow mobilization time is a contributing factor. GNSS techniques in comparison are quick and easy to set up, requiring at minimum a rover and potentially a base. They do also, however, require physical contact with the area and are also a slow process, recording each individual point. Post-processing is also required. Now, comparing to total station and GNSS methods, UAV techniques show an ability to cover large areas quickly, however have an intense post-processing system as large amounts of data are captured. This also requires large amounts of computing power. UAVs can also be quickly deployed, reducing overall field time.
Finally, a case study will be analysed, specifically an agricultural example of palm oil plantations in Colombia. Colombia is the fourth largest producer of palm oil in the world, hence it is a massive contributor to their economy. The plantations cover vast areas of land and are affected by natural phenomena including plagues, storms and lightning strikes. Therefore, a number of palms can frequently change and hence affect money, time and resource requirements. Conventionally, to track these changes, workers would walk through the plantations and count the palms, recording by pen and paper the number. This method was hindered with human error and also time. Companies attempted to use satellite imagery, but the characteristic cloudy weather of the tropical regions and the higher price of acquiring imagery has prevented these methods from being cost effective. Companies are now trying to use UAVs to fly over plantations, using photogrammetry software to create orthomosaics and use detection and counting software to count the palms. Due to UAVs having a wide Langle lens, there was large distortion in the images. Due to the multi-rotor UAV being used and a flight path also being used to capture these images, all photos were taken at the same height with a constant percentage overlap. This allowed the photogrammetry software to create orthomosaic images. Overall, from this case study it can be seen that UAVs can be a good choice in counting palm oils in plantations because it is cost effective, safer and a much more efficient method than conventional methods of counting. Palm counting has also been used in the citrus industry with good results. Overall, UAVs are becoming an integral part of the surveying industry and provide surveyors with another tool to achieve the best outcomes for their clients.